Sorry for the late start. Welcome to the last week of the lecture series of intelligent systems. Thanks for coming. Sorry that I started a little bit late. I've just uploaded the slides for people who want to read the slides on their own screen or make notes. Today I'm going to talk about machine learning, and today is going to be a more general introduction to some basic concepts of machine learning. Tomorrow I want to get into more recent developments and a bit more calculus and neural networks. Maybe not the best summary for tomorrow, but so tomorrow is a more technical introduction into machine learning. And on Wednesday morning, the first hour I want to talk about deep learning, just to give you some idea, some intuition of these concepts that obviously are now very much in the media and so forth. You will have a course next year in machine learning which covers all these concepts in depth, but it's still, I think, quite important to have seen them also a bit earlier. We'll, in the second half, I want to practice a little bit just to get an idea of, with one of the more old-fashioned, but still very useful classifiers-based classification based on the Bayes rule. And then in the end, I want to talk a little bit about how we can apply machine learning to our own intelligent agent, to the game engine. So that's the plan for today. I hope that you all sort of are happily hacking away with intelligent agents playing Schnapsen, and that you have some successes beating the random bot. If you're still not outperforming random bot, then you have a problem or we have a problem, but this is the kind of challenges you face when you do research in this area. So it can well happen that you come up with an idea, and if it doesn't work, it doesn't work. So that's research. One of the things we can do is that to all the agents that we have built now, we can make use of them, and the way the strategies they play, or the way they run the games, that we now sort of build previously played games and translate them into machine learning models so that they can help us predict. And that's why predict which the best card to play would be, or the best strategy to play in the game. So that's why machine learning is obviously a very important part of any intelligent systems course, but particular one where our practical is based on real intelligent agents that are playing the game. It really is very interesting to investigate whether learning from previous experience for other games is useful or not. And in order to be able to do that, before we can move to that at the very end of this lecture, I want to go through some of the basic concepts and sort of remind you probably of the general ideas of what we're talking about here. So this doesn't look too good. It's not moving. This looks better. So I want to start with an introduction to the main concepts of machine learning, later some methodology, and then some simple example with naive Bayes learning. So if you have, unless you've sort of sat in a cave for the last year, if you've ever opened a newspaper a bit more regularly the past month and year, you always come across machine learning AI applications. So it really has become mainstream. So if it is algorithms that turn photos from politicians into Halloween pictures, which is based on deep learning technology, whether it is photo apps that do some profiling willingly or unwillingly in a particular way that one wants to have or not. If it is a robot that sort of predicts ways of how people will pour beer, it really has come to the mainstream and is reported regularly in the media. And it went so far that most people nowadays, whenever they see something machine learning, it's just called AI, so, or the other way around. Most AI applications are now so deeply built in machine learning ways, so that these are really extremely important concepts in society nowadays, not only in the science that we are living in. So, starting from the intelligent agents that we discussed in the first week, we obviously would like our Hoover to go through our house or the view in some intelligent way, deciding where should I go, maybe learning the map, making some model of the map that in which it investigates, in which it maneuvers, then learning where is the most highest probability that there will be dirt, where should I go more often, where are some dangers that I don't go down a staircase that I can't get up again, and so forth. Why is it useful? It's useful because you don't want to program the environment into this Hoover in the first place, so it makes it far more easy from a perspective of engineering such a tool. It makes it more robust, so if the environment changes, if you would deliver a robot for cleaning the view with a map of this building, fine. But if next day someone comes and puts something in the middle of the room, then the robot wouldn't know about it. So it would be good if the robot could itself learn how this environment is built. So it's from an engineering perspective, it's good to build from an adaptivity perspective, so it can change when the environment changes. Basically, this way of thinking of learning is called online learning, because you are in the environment and you try to understand more about the environment and to perform better the more you live in this and perform in this environment. And the way this is nowadays mostly treated is called reinforcement learning, and unfortunately I won't have time to get into reinforcement learning, but I guess that this is something that will be covered next year in the machine learning course. What we are focusing on here, because this is also sort of one of the basics and enough for 2.5 days of lecture, is offline learning, where you get some kind of training up front, and then you make your decisions based on this training and the models that you built during this training. So we won't get into the adaptive intelligent online decision-making world, but do our training in an offline case. So still, even in this offline case, the questions are relatively generic, always the same type of questions. Which components of the performance elements are to be learned? So what exactly do I want the robot to learn? It should go from place A to B, where it can go from A to B, and it should hoover particularly at the places where there is most dirt. So it's the two things: maneuver from A to B and hoover. It doesn't really matter how much noise it does or how much electricity. So maybe it could also play music, but that's not what we're going to optimize it for. It really is the hoovering that things should be clean. What feedback is available? The hoover bumps into things, it has sensors, it knows whether things are clean or not. And then the question is what representation is used, and that's something we'll look into in more detail later in this lecture. And what the agent sort of does is learning properties about the world it performs in. It might also learn more information about the success it has, so things becoming more clean and so forth. It can also learn its own behavior, so more in a genetic algorithm way, that if it takes certain actions, things happen. So that is the reinforcement paradigm, that you get some feedback that things change according to your actions, and then you can adapt your actions. And you can also learn maybe what your goal is. Maybe in the beginning you don't even know which of the things are really your success to which you optimize. So if we now would send a robot to Mars, we might not know precisely what things it could find that could be interesting, and maybe it could learn it automatically. It could improve its sort of curiosity as one of its learning goals. We will focus on offline learning, so there are some training examples, and you want to make predictions or classifications on the basis of the known knowledge that you have sort of somewhere represented, and you want to apply the machine learning model, the thing you have learned, to new and unknown data. That's basically the very simple task that we are focusing on and which is already extremely useful. So the classical thing is recommendation. We all encounter it very often, and if you use Netflix or Spotify or whatever, you always get things that are recommended on the basis of already existing data that is collected about yourself, but also about other people. And what we also apply is an idea of supervised learning, and there is a beautiful old movie that sort of explains this idea. I really think is very cute, that you should look at. I hope it works, the sound. It's not working very well, is it? So, let's try again. You guys still can't hear it?
Is being trained to recognize the difference between males and females. It is something that all of us can do easily, but few of us can explain how. To get a computer to do this would involve working on many complex rules about faces and writing a computer program. But this perceptron is simply given lots and lots of examples, including some with unusual hairstyles.
But when it comes to a people, the computer looks at facial features, the hair outline, and takes longer to learn what is told by Dr. Taylor. And people so called as little heart searching.
After training on lots of examples, it's given new faces it has never seen, and is able to successfully distinguish male from female. It has learned. While promising, this approach to machine intelligence virtually died out.
Where is mine? Here we are. So the last thing they said, I'm not sure whether you could understand it. The last thing they said was unfortunately this way of thinking in AI almost died out. We'll get to that tomorrow. The neural network winter was a way where this very promising technique seemed to not work properly. And as we know now, there are some technical improvements on the technology that now make this the core of machine learning in general. Why I showed the video is that it's a very nice example of a typical task of offline learning and a specific type of learning and classification. You take some existing examples of images about men and women, and you train them on known images, and then at the end, once you've learned a model, in this case this was a neural network, once you've trained the neural network, you show it to, you give it some unknown new examples, and the machine tells you whether it's a man or a woman. And that is obviously something that AI was interested in right from the beginning. So in the 50s, they came up with this algorithm, and it worked. The big problem then was that it doesn't really scale, and that has now really been addressed properly, and we're going to talk about that tomorrow. So in this case, there is a sort of a feedback that's given to the machine. You have an example, a training example, and you give it a label which says, okay, this is a man, this is a woman, and it's about learning this label. So if we have this feedback, we talk about supervised learning. If there is a training set of someone that usually humans say up front, okay, this belongs to one class, this belongs to another class, or this has this function has this value that you should learn, or this element has a certain value about the instances. You sort of give the computer the target, and then it is about to learn the target automatically, and that's called supervised learning. Unsupervised learning is if you don't have that, and we're going to look into one of the examples of unsupervised learning also tomorrow. Clustering. Sometimes you have semi-supervised learning where you don't have any classes to start with, but you have a human in the loop which might ask questions to help you. So active learning is one of these tasks. And reinforcement learning is if you perform somewhere in an environment and you get occasional rewards. And I will probably mostly focus on the first part and very, very briefly look at the second one, the unsupervised learning. So let's look at three sort of typical canonical examples that have made the news the past years. So the first one is handwriting recognition. So nowadays, computers are pretty good in recognizing handwritten texts and really turn them into digital representations that are understandable. So, and that is usually done by training. So you are supposed to write in your own handwriting some words that are given, and once you've given the computer more examples, then it can recognize this automatically. Chess was an example where there was a lot of strategy learning. So basically what IBM did at the time was to take huge databases of chess games, complete chess games, and just learn what an expert human player would do in certain situations, and then basically took this as one of the bases of the algorithms that in the end managed to outperform humans by far. And the next one is the automatic car, which nowadays drives through the cities of even, I think, the Netherlands, at least for test purposes. And these are sort of three canonical, very typical examples of where machine learning is applied, but also examples where you can apply the canonical tasks of machine learning, such as classification and regression and so forth. So in the first, in the handwriting recognition, you give it some letters, and you tell it that this letter is supposed to be an M, whatever, and you give it thousands of them. And then the model is trained on existing handwritten text to produce the digital version of it. So this is a typical classification task. Give it some trained examples where each of the letters is an element of one class. If I write down this on the board, you all probably think that this might be an instance of the class object M, so we can use it for training for M. And good algorithms would then recognize that this should be an M. Yes?
In handwriting, it happens that sometimes we write something, and when we introduce a new sign, and when someone is reading, you can just read that this sign means something. But when we make the computer recognize it, then there's a problem that this sign should be just omitted or wrongly classified.
Yes, I guess so. The point was that we as humans, if we get a new sign, we can still continue reading text, but the computer then sort of gets confused. Unless you have it trained on this new information, and it will get probably used to this very fast. So I'm sure that this won't be a problem anymore at the current state of technology. The same thing happens with classification. Is also one of the core tasks of the second example of chess playing, because it's a very complex classification task, basically, where you have to say, I have maybe 20 moves given a state. Which of the moves should I take? And you can take each of the moves as a state. So that might be not the most of the clever ways of doing it. Another way, and we look at that when we look at Schnapsen and how to use learning in Schnapsen. Another thing is called value learning, where you try to estimate the value of the heuristics. So then we basically have a regression problem. But I get to that in a minute. And even for the car, you can sort of reduce this to a classification problem, because according to the situation and the observations that you have, you need to make the decisions, go to the left, go to the right, or go straight on. You might have a bit more detail, but it's surprising how little you basically need to in the main in the big decision making on the top level of the decision making. So basically, we see that many of those tasks can be reduced to some canonical machine learning problems, classification, regression, and the machine learning research is on the methodological side. So we have a very strong machine learning group at the UvA, for example. They sort of don't bother that much thinking about, am I now doing image recognition or dealing with a chess play? They look at the more abstract level at classification in general. So here are some of the typical types of machine learning tasks. We have classification. So the input is an instance with some information about the instance, and the output of the algorithm would be which class does it belong to. And this class could be binary, just true or false, or it could be could be discrete number of finitely many values. Regression is that you want to learn a function that describes values of the individuals. Ranking is simply sort of you have two instances, which one is better. Collaborative filtering is give me some information about previous experiences and make suggestions of new things. And clustering, as I said, is the only non-supervised approach here. But that's now on the problem side. So let's look at some examples of these problems. So basically, the classification task is to go from data to discrete classes. And handwriting, as I said, is one of them. So this is an example of a huge training set of thousands and thousands of letters that have been written and mapped to some ASCII code, I would guess. And the task is just give me one of those letters and tell me whether it's a 2 or a 7 and so forth. Another one we encounter every day is the spam filter idea, that based on the use of text and words and orders of words and letter types and so forth, we can detect whether certain things are spam or whether they're not spam emails. And again, in this case, this is where we have two classes. If we learn numbers in handwriting recognition, we have 9 digits. If we have the alphabet, we have 24 letters and so forth. So that becomes then more difficult in a way. If you have face recognition, you want to distinguish things from faces from other things in the images. So that's also a classification problem. We have to say, okay, we've recognized an object in the image. Is it a face, or is it a foot, or is it a football? So again, it's another classification task, but now with many, 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 many classes, unless we have a classifier that only distinguishes faces from anything else. But if we want to have object recognition, then we have many more classes. And if you want face recognition to also recognize who this person is, then you usually have a database with many classes of people that you're looking for, and you want to match the object with some data in your training set. You can even think of weather prediction. So if we have just to predict whether it's going to snow or rain tomorrow, then this is a very simple classification task. Simple in the sense of what the task is, not that there is a simple solution to it, of course. So here's the driving car example, why this is even to be considered a classification problem. And this doesn't come out very well, this example, but this is a driving car from 1995, and it was able to drive without a driver, so pure AI from the east to the west coast, I believe. There was a human there. I think the human was executing the commands from the computer, so it wasn't integrated. But basically all it had was a camera that was taking a very, very bad picture, 30 by 32 pixels. And it had about 960 features in altogether to sort of identify where a street was. And basically all it did was command go straight, left, right. So it was a classification problem of a situation where we had 960 features, 960 values that were measured at each decision point. Yeah, so if it's just a pixel. You're right, absolutely, yeah. So it's just the pixel as input. And then the decision is taken left to right. So there isn't even any qualitative
it's not in grayscale because it was color. You would multiply it by even more.
Yeah, it probably was black and white, yeah. And even that worked, and I take this example to show that even the more complex problems such as driving a car, part of the functionality of this AI can be really reduced to, in this case, a classification problem. So this was some examples for typical examples for classification. Regression is another very typical example where you have where you want to predict a numeric value. And that would think of the stock market. I think that one of the famous examples where prediction, unfortunately, doesn't work yet. So there has been a lot of effort taken into, but machine learning efforts are notoriously bad at predicting unexpected behavior, and obviously the crash of the stock markets are always sort of the result of a complex system performing a non-predictable result. So in that sense, stock market is a huge challenge, but what you basically would like to know is if the stock market runs for another half year, will this stock go up or down? That would, of course, be a learning problem, and what you would want to learn would be a function for a certain product or a certain company on the stock market. We have said that the weather prediction could be a classification problem, but it can also be a regression problem, where you want the output to be the temperature, for example, at a certain time. All these things are related, of course. So you could say I only look at 50 natural number values of temperatures, and then the regression problem would be a classification problem. But in a way, there is in this case, it really is a logical way to see, to look at temperature prediction as a regression problem, so as a function assigned to time points, for example. You can also use information about this function or about classification for ranking. So the task is here that you want a web search. So which of the websites that a web search should return is more relevant to others. So you get maybe things that have the same relevance according to the words that occur in the website, but it should be that some pages are more relevant for me than for other people, so it would be interesting to have a ranking that gives me different results at the top than other people. And so if you have notions such as trustworthiness or popularity, then obviously you can learn this, for example, if you have training data as a regression problem, and then translate the regression results into rankings. But from the task perspective, this is simply a different task of machine learning. Similarly, you have a certain picture and you want something that's similar. So a notion of similarity is typically something that is useful for ranking. Collaborative filtering is something we have every day. We come across. So when I buy something, there is a recommendation on Amazon telling me that many people who bought similar products bought something. Don't you want to also buy this wonderful product? And then there was this challenge some years ago. I don't know whether it was solved or not, to be honest. But there was that Netflix obviously is one of the most important things of Netflix is that it provides films and series and so forth, but that it also recommends new things to the people who view. And this is a very complex thing. So how can I recommend to someone which film to watch on the basis of what I know about them? And you know something about the personal information that you might collect, but mostly you know what kinds of films they have watched. But now the question is what makes a good prediction for the next film to watch? And I'm so annoyed when I book a flight to somewhere. So I buy a flight to Vienna, and the next day I have an advert on my website which says, oh, don't you want to buy a flight to Vienna? Yeah, sure, I've just bought a flight to Vienna, I don't need to go to Vienna anymore. So it's very difficult to understand what the task is in the first place. And if you are only recommended things that you have already seen, that's not a good recommendation. So they had a competition where people who came up with the best machine learning algorithm would get $1 million prize. And as I said, I don't know how this competition ended, but it was it really was something in the media for some time. And finally, as I said, discovering structure and data. So you have some data points with some properties X and Y, and you would probably say that these points probably share more properties than the points on the top. And this is a useful thing if you have an image database, a set of images, and you want to cluster them according to some features that you might not know up front because you don't know what's on the features, on the images. So you might have one bag of images that has animals and the other one has houses. But we can't make a classifier out of this because then we would have to know upfront all the topics that are on the images. So in a way, this is classification without the target given. And that makes it very difficult, not so much to learn, but particularly to evaluate. So what is a good cluster of images? So if I would give you 100 images and I would give you 100 images and say cluster them into clusters, you would probably come up with completely different ways of clustering. So you might have split them into black and white and color, and you might have split them up in animals, houses, and many more smaller clusters. So it's very difficult to say this one is better than the other one. But we're going to discuss it later. And I'm not sure whether anybody uses this kind of technology, but it was around when I was a bit younger, that when you did a web search, you didn't just get your favorite websites first, but you also got them clustered by some topic that they were about. So this website, Cluster, did this search for you and then also presented the results of your search according to some feature space. Okay, so that was probably not too much new things, apart from the fact that you can usually translate many problems into these canonical machine learning problems of classification, regression, clustering, filtering, and so forth. And that in principle, there are very few tasks nowadays where learning cannot contribute at least a little bit. So now let's move from the application side to the development side, and let's assume you want to play around at least with some machine learning technology algorithms, and let's see at classification and how what you have to do in order to sort of apply these things in a valid way, these tools in a valid way. And that's sort of the basic machine learning pipeline for classification now with supervised learning. So basically, you begin with data, labeled instances. So for example, emails that are marked with spam or not spam. And what you usually have to do is to test the model that you have trained on some unseen data. So you get one bag of data which is labeled, and you usually split it in some way. So you split it in testing data and training data. And there are some heuristics for that. So often you split it in 60-20-20. And the idea is that you have need a lot of data to train, so that's usually 60%. And then you have 40% on which you put aside in some extra file, which you don't look at. And later you want to evaluate your algorithms on. But you might even need more things in between. If you do some in between evaluation where you say, okay, I've now tuned my system to a certain point, does it work or not? And therefore you have this held out set or the testing sets. You first test it on some data, which then also helps you to improve your model. And in the end, when you then want to tell, okay, my algorithm works, you really have to test it on unseen data, unknown data, and see whether it indeed performs very well. So that's one of the core laws of machine learning experimentation is never evaluate on training data. So if you want to report the performance of your systems, you always have to do it on unseen data. It sounds trivial, but you cannot imagine how many papers have been published where some kind of training data has creeped into the testing sets, and then obviously the systems perform wonderfully well because they've seen the data before and they've been tuned to this data. The thing we are going to talk about a lot is the features. So they are usually attribute value pairs that characterize each of the objects in my training data. And that is basically the image that we've just seen with the driving car. Each of the pixels of the 30 by 30 can be an on or off. So that would be an attribute value pair that pixel 00 is on or pixel 00 is off. But it can also be a word that occurs in a text for classification, or it can be a pixel in the image recognition where there is something written down or not. But we're going to talk about features and how to organize them, how to define them, and this is one of the main tasks also for Schnapsen, that you have to think about your feature space and what you can do, how you can make this as information rich as you can for your machine learning model. And then the question becomes, how can we, based on the data that we have seen, how can we write an algorithm that, that it performs as well as possible? And that basically turns out to be a search problem of hypotheses that we can give. And I'll show you tomorrow one where you basically try to find a point in a two-dimensional space or three-dimensional space with specific properties, and it becomes a search problem. Once you've sort of trained your model, you have to test it, and you have to calculate the accuracy of it. And that is again what I said. So that is the deadly thing. Never peek at the data. The testing data. If you want to report on the quality of your new model that you've trained, it always has to be on completely unseen data. And then basically you can report on the quality of your classification in this sense, using some notions of accuracy or recall. So accuracy is the fraction of instances that are predicted correctly. We also have the notion of recall, which is how many of the correct instances have been classified correctly, and precision is how many of the instances that are returned are correctly classified. So that's the typical things that you have in the evaluation phase. I gave you the example where you split the data set upfront into a training set and a testing set. Here's another methodology that is very often used and that's very useful, particularly if you don't have that much data, that you perform your experiments several times. So you train your data on 80%, you train your model on 80% of the data set, and then you test it on 20%, the remaining 20%. Then you take another 20% of the same data. We're still busy with the same data. We'll take another 8%, but now different in the sense that we have a different testing set taken out. So basically, you split your data set in 5 big bits, and you train always on 4 of the 5, and you do that 5 times with different things that you take out. And that's usually called cross-validation. So this would be, in this case, a 5-fold cross-validation because you take 5 of these folds out, and then basically you average over the error or the accuracy and so forth. So that's a technology that's also very often used, and you will see that in reporting in the literature. And then the basic recipe for doing machine learning is, I think, fits very nicely in the structure that we applied in this course from the beginning. Namely, you choose a feature, so you decide on what is it that I know about my object, which I want to train and which I want to do the prediction later. What kind of model do I want to apply? And I will make that concrete after the break. And then at the end, this is translated into a search problem. So how can I find, of all the possible models that are around, how can I find the one that is the best one to predict on new examples? And I want to show you